So now we're going through some of the solutions to the test 2. The other solutions you can get off of the week 16 module under supplemental videos. So here says find the local and absolute maximum and minimum, right, for the following function and where they occur. If the function does not have an absolute or local extreme, explain why. So we're given f of x is equal to 9x all over x squared plus 1. And so first thing that we want to do is we want to find the derivative, and we need to find our critical values. I notice here that f of x is defined everywhere, because if I look at my denominator, x squared plus 1, there's no value which sets that equal to 0. If I factored that or I solved for x down there, that would give me an imaginary number. So domain is all real numbers, and we're going to look at the derivative. And looking at the derivative, we need to apply the quotient rule. And so the quotient rule says the derivative of the numerator, which is 9, times the denominator, x squared plus 1, minus the numerator, 9x, times the derivative of the denominator, which is 2x, all over this denominator, x squared plus 1 quantity squared. So let's just clean this up a little bit and combine like terms in the numerator. So distributing that 9, we get 9x squared plus 9. Distributing the 9x to the 2x, we get minus 18x squared, all over the denominator, x squared plus 1 quantity squared. That denominator is quantity squared. Combining like terms in the numerator, we have a 9x squared minus an 18x squared. So that gives me a negative 9x squared. I think I'm going to write it as 9 minus 9x squared, just so the positives first, all over x squared plus 1. And that x squared plus 1 is quantity squared. So now I also notice that I can factor out a 9 in the numerator, but I also can do that when I'm just sitting here looking for when is that derivative equal to 0. So we're looking at a rational function. All we're really worried about when that's equal to 0 is when the numerator piece is equal to 0. Or think of it as I'm multiplying both sides by my denominator. The denominator would clear on the one side and times the 0 on the other side is 0. So we're really looking at when is 9 minus 9x squared equals to 0. A couple ways you can solve this. You can use the square root method by isolating your square because it's set up in that form to do so, or we can factor. So if we pull out a 9, this gives me 1 minus x squared equals 0. I have a difference of squares. So 1 minus x, 1 plus x equals 0. So I can see x equals 1 and x equals negative 1 are values what set this equal to 0. So let's look at the intervals on each side of our critical numbers and see if it's increasing or decreasing there. So we have two critical numbers, -1 and 1. So let's choose something to the left of -1. So x equals -2. And we're plugging it back into the derivative to see when we plug it in, is that value going to be positive or negative? So if I plug in -2 into that x squared in the numerator, I get a 4 times the -9 in front. So that's 4 times -9 is -36 plus that +9. So that's a negative number. I'm really just curious, is that going to be negative or positive? Notice that denominator. That denominator is quantity squared. So if we square a positive or a negative number, we're going to get back a positive number. So that denominator is always going to be positive, no matter what number we plug in there. So I see that this is less than 0. And so we're decreasing from -infinity to -1. So now choose a number that falls in between -1 and 1. So 0 is there, that's usually the best one to choose. And so if we plug in 0, and it's defined there, we get 9 in the numerator. So that's positive all over the denominator, which we talked about is always positive. So this is greater than 0, this is increasing. choose something to the right of x equals 1, we have x equals 2. And plugging in 2 into the derivative, we get a negative number in our numerator over a positive, which is less than 0. So this is decreasing. So it looks like we have a local max and a local min. So something that's coming down and decreasing to increasing is a min. So we have a min at x equals -1. In a minute, we'll find out what that point is. And we have a max at x equals 1. Let's just think about this graph just a little bit. And so if we're decreasing, we're going to come down and then we're going to hit -1. We're going to turn around. We're going to hit +1. We're going to turn around. And then we're going to continue down forever. So if we think about this and we think about our end behaviors, look at that the limit when x goes to -infinity of our function f of x, this is +infinity. So there's no absolute max because of that. That continues to grow upwards. There's no highest value that will ever hit. Same sort of reasoning when we're looking at the limit as x is going to +infinity of f of x. Our y value is shooting down to -infinity. It's never hitting a smallest y value. So there's no absolute max or absolute min. So we need to go in here and so this was decreasing. It's also decreasing from 1 to infinity. I guess I don't need to really write that stuff because that's not what it's asking. So we're finding now the local extrema, and it said where they occur for the following function. Okay, so find them. So the local extrema, that is where the y value is. So we need to go back in and plug this into our original equation. So our original equation was f of x is equal to 9x all over x squared plus 1. If we plug in -1, wherever we see an x, we get -9 in the numerator, all over -1 quantity squared is 1 plus 1, so 2 in the denominator. So at the point -1 9/2, -9/2, this is a absolute or a local min. Minimum value of -9/2. And if we plug in +1, wherever we see an x in our original f of x function, we get back 9 all over 2. So +9/2 is our local max, and the point occurs at 1 +9/2. Okay, so that was that problem on the exam. Let me see if there's any questions before I move on. So this was a similar problem on the other version of the test. So same sort of idea. We're trying to find absolute max, absolute mins, or local max or mins. And we have a rational function. We're going to start again by taking the derivative, which again, we need the quotient rule. So the derivative of the top, which is 1 times the bottom, x squared plus 2x plus 2. Minus the top, x plus 1, times the derivative of the bottom, which is 2x plus 2, all over the denominator, x squared plus 2x plus 2, and that denominator is quantity squared. So let's distribute combined like terms in our numerator. And so that first piece, distributing on 1, just gives us that x squared plus 2x plus 1. Sorry, not plus 1, plus 2. Minus, I'm going to put brackets here because we have to distribute and then we can get, distribute that negative. So if I distribute out this x to 2x plus 2, I get 2x squared plus 2x. Distribute my 1, I get plus 2x plus 2. All over our denominator squared. So I have x squared plus 2x plus 2. I'll only have a negative, so distributing the negatives, this is a negative 2x squared. Right here, this 2x plus 2x is 4x. So when we distribute that negative to that piece, that's going to be a minus 4x and then a minus 2. All over the denominator squared. And we get negative x squared, a 2x minus a 4x, a minus 2x, and a 2 minus 2 is 0, all over x squared plus 2x plus 2, quantity squared. So now we want to find out when this is equal to 0 and where it's undefined. And so setting the numerator equal to 0, let's factor out an x from each of those terms. How about let's factor out a negative x from each of those terms. So if I pull out a negative x from negative x squared, I will be left with a single x. If I pull a negative x out of a negative 2x, I'm left with a plus 2. All over our denominator squared. So I look at my denominator to see if I can factor that, but there's no two integers that multiply to 2 and add to positive 2. And so that doesn't factor over our integers. I should look to see if there's any real number that sets this denominator equal to 0. So I don't know if you guys remember that discriminant property, where if you look at what's underneath the quadratic, in the quadratic formula, what's underneath that radical, if you basically find out that sign, you can tell if there's going to be how many solutions of what type. And so if I look at my b value, which is 2 in this case, 2 squared minus 4 times a in my case, down in the denominator, that coefficient in front of x squared is 1, and c is 2. So notice that this number 4 minus 8, that's a negative number. So that's going to give me a negative under my radical, which is imaginary number. So there's no real solutions. So there's no real number that sets that equal to 0. So it's defined everywhere. So I don't have to worry about what values of x make this undefined. So again, we're looking at when is f prime of x equals 0. And so again, we're only looking at when is our numerator equal to 0. We already factored it, so we can set each factor equal to 0. And so negative x is equal to 0 when x is 0. And x plus 2 is 0 when x is negative 2. So let's look at our number line. Let's plot those values. So negative 2 and 0. We're going to go in here and we're going to plug in numbers into the derivative to see if we have a positive or a negative. And so if we choose x to be less than negative 2, so how about negative 3? So plugging in negative 3, wherever we see an x in here. So I would get negative, and then I would have that negative 3 part just squared, which is 9 with a negative in front. So that's going to give me a negative 9. And then negative 2 times negative 3, that's going to give me a plus 6. So see, it's negative on top. Denominator, though, that whole denominator is squared, so it's always going to be positive. So negative over a positive gives us something that is less than 0, so it's decreasing there. Choose something between negative 2 and 0. So how about x equals -1. So if we square -1, that's 1 with a negative in front. Is negative. And then we're going to have -2 times -1, so that's +2. So we have -1 plus 2. That's a positive number in the numerator, always positive in the denominator. So this is going to give us something greater than 0. So it's increasing. Choose something to the right of x equals 0. So how about x equals 1? Plug it in. We get negative and then 1 squared. So that's -1. And then we have -2 times +1, so -2. Our numerator is negative and our denominator is positive. So this is less than 0 and it's decreasing. So looking at this and knowing it's defined everywhere, decreasing to -2 and then increasing after -2. So we can see that there is a local min at x equals -2. And then we can see there's a local max at x equals 0. Again, thinking about the graph to see about absolute max and absolute mins. If we have something that's decreasing forever until we hit -2 and then coming up and then turning back around and decreasing forever, notice that that is not going to have an absolute max or absolute min. So because of the graph, no absolute max or min. And then to find those values, you're plugging it back into our function of f of x. So again, f of x was equal to x plus 1. All over this x squared plus 2x plus 2. So if I look at f of -2, going in and plugging a -2 wherever I see an x, -2 plus 1, that is a -1 in the numerator. All over -2 quantity squared is 4, plus 2 times -2 is -4, so those cancel, plus 2. So we have 2 left in the denominator. And so local min is -1/2. And we can say the point is -2, -1/2. And then we know that there's a local max at 0. And so plugging that 0 back in the original. Well, 0 plus 1 is 1, all over 0 plus 0 plus 2. So 2 in the denominator. So the local max is 1/2 at the point 0, 1/2. So you should be able to, on the final, be able to find local extrema and absolute extrema. You should be able to find where things are increasing and decreasing. And you shouldn't be able to find derivatives using all of the different properties. So here's one problem that shows me you know how to use the quotient rule, you know how to find where it's increasing, decreasing, find critical points, and find your local and absolute extrema. So one problem tying in a lot of different concepts. And that's basically what's going to be happening with all these questions on the final, where we've been building pieces this whole semester. Okay, so the next problem that wasn't on the other video is the following. So if the derivative of f of x, f prime of x, which is equal to 12 times 4x minus 5, and that 4x minus 5 is raised to the -6th power. We want to find f of x, and we're given that f of 0 is 1. So what we need to do, we're given the derivative. In order to find the original function, we need to take the antiderivative. And so we can say that, well, f of x is equal to the antiderivative of f prime of x, which is this 12 all times 4x minus 5, all raised to the negative 6 power dx. So it's not in a form that I can just go ahead and integrate right away. I need to use some substitution. And so I noticed that I know how to, if it was just x inside of that parentheses, x to the negative 6, I could take the antiderivative of that. But because there's this 4x minus 5 in that parentheses, that is making it difficult. So we're going to let u equal this, what's inside the parentheses here, 4x minus 5. Differentiate both sides. Derivative of u is 1 du equals the derivative of 4x minus 5, which is 4 dx. So we need to figure out what dx is in terms of du. So divide both sides by 4, we get dx is equal to du over 4. So now we're going to go back in and plug in what we had chosen to be our substitution. So we have u raised to the negative 6 power times dx, but dx was this du over 4. So notice 4 goes into 12 3 times. If you want, if it helps you, pull the 3 outside of the radical. And then we're just left with u to the negative 6 du. So we can take the antiderivative of u to the negative 6, add 1 to our exponent, we get negative 5. Divide by our new exponent of negative 5, plus some value of c. We're going to find out what that c is because we've given this up here. That f of 0 has to equal 1. But before we do that, we need to rewrite this back in terms of x. 3 times negative 5. So this is the same thing as negative 3/15. I'm sorry. No, it's not. Negative 3/5. Let's just bring that u down to the denominator and raise it to the 5th power. But u was this 4x minus 5. And then we have plus c. So we know when x is 0, that y is equal to 1. From f of 0 equals 1. So plugging that in, we got x is 0 and y is 1. So we have 1 is equal to this negative 3 all over 5 times, well, 4 times 0 is 0. And then we have this negative 5 to the 5th power plus c. So clean it up a little bit. Well, if I take negative 5 and I raise it to the 5th power, that's still going to be negative. And so I can pull that negative out front. And then I have 5 times 5 to the 5th, which is really 5 to the 6th power plus c. So c here is equal to 1, but this minus and a minus is positive. And if I subtract that on the other side, minus 3 all over 5 to the 6th. Okay, so we have to figure out 5 to the 6th power, and I did not let you use a calculator on this. And so let's just start going through. So 5 times 5 is 25. 25 times 5 is 125. So that's 3 of them. Well, we need 6 of them. So can't we just group the other 3? 5 times 5 is 25 times 5 is 125. So we could technically look at 125 times 125. And I didn't realize that this one was so long. So 5, that's 25, that's 10, that's 12, that's 6. So 0, 10, 4, 2. I'm just multiplying. Adam. I did everything right. 15,525. So 15,525 over 15,525, same thing as 1. And then on that numerator, subtract 3 from it. So that's going to give us 15,522 all over 15,525. So that's our C value. So f of x is equal to -3 all over 5, parentheses 4x to the -5 power raised to the 5th, plus c. So plus 100 or 15,522 over 15,525. So there's a, let me just look real quick. So similar problem for the other version, which is version A, f of x. We're given the derivative of f of x, f prime of x equals 16x, all times 4x squared minus 1 quantity cubed. Find f of x as f of 1 is -1. And so notice here again, we are given the derivative. To find the original function, we're going to have to take the antiderivative of our derivative function. I can't go ahead and integrate this right away. I need to use U-Substitution in order to do this. So we're going to choose our U value to be what's inside the parentheses again, which is 4x squared minus 1. Take the derivative of both sides. We get du equals 8x dx. And dx then is du over 8x. So when we go back in here, and I forgot to bring down this x in here, so this should have been 16x in front. So when we go in and substitute, we get 16x all times u, quantity cube, and dx is du over 8x. And so notice that 8x goes into 16x twice. We can pull that 2 out in front of the integral if you want. So all we're integrating is u cubed du. So add 1 to our exponent, which is 4. Divide by our new exponent of 4. So, and then plus c. That reduces a little bit. 2 goes into 4 twice. And then we can go back in and substitute what u is in terms of x. So u in our case is 4x squared minus 1 raised to the 4th power plus c. So far this is f of x. We just need to figure out what c is. And again, we have some information. And so this is saying when x is 1, y is equal to -1. So let's plug that in. So we have -1 is equal to 4 times 1 squared minus 1 to the 4th plus c. So we have -1 is equal to 1 squared is 1 times 4 is 4 minus 1 is 3. So 3 raised to the 4th plus c. So 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th is 81 plus c. So if we subtract 81 on both sides, we get c is equal to -82. And so go back in and plug it into our f of x function. We get f of x is equal to this 4x squared minus 1. That's all raised to the 4th. Oops. Forgot my divided by 2. So there should have been a divided by 2 here. Thanks. From here. Divide it by 2. Divide this by 2. That changed this things a little bit, doesn't it? So divided by 2. So if I subtract 81 halves, and -1 is -2 halves. So -2 halves minus 81 halves. This is actually a -83 halves. Wait a minute. Yeah. Is equal to C. So minus 83 halves. I forgot it again. So this divided by 2. So technically we could rewrite this as a single fraction if we wanted, but we can leave it like that too. Okay, so the next problem says for the integral evaluated from -4 to 6 of the integrand x squared plus 7 and then times dx, answer the following questions. Graph the integrand and approximate the area under the curve and the x-axis by using 5 rectangles of equal width. Okay, so if we graph this function, we are looking at the function of f of x, which is equal to x squared plus 7. So I'm going to just use some of my algebra to be able to graph this, but we could use our tools of calculus to find where it's increasing, where it's decreasing, where is our min or max. But I know that this is a parabola, and I know that a parabola at x squared, the vertex is at 0, 0, and this plus 7 is shifting me up 7 units. Or we could use rules to find the vertex using algebra. But basically I have a parabola which is facing upwards. And the vertex is at 0, 7. And then I am starting at x equals -4. So 1, 2. And I'm ending when x is equal to 6. And my thing is not gonna be in scale, just of how I wrote it, but maybe I can just make this wider. Okay, now that's better. And so we want 5 rectangles of equal width. Well, we need to figure out what is this length in here. And we can do that by looking at our b value minus a. So we have 6 minus a -4, which is equal to 10. And we want to split this up into 5 triangles. So divide that by 2. I'm sorry, divide that by 5, and we get back 2. It didn't tell me if I'm using which height I'm using, and so it's up to you on which you use. I didn't realize I did that. Okay, so I can either, this width has to be 2, starting at -4. So adding 2 goes us to -2. I can either have the height of my rectangle be this left-hand side when I'm hitting the graph, or this right-hand side. So you got to just choose one. So let's just do the left or right. Oh, that's the right. So I'm going to look at this area. Well, that's 2 times, this is f of -2 right here. Well, if I plug in -2 wherever I see an x here, I get -2 quantity squared is 4, 4 plus 7 is 11. Okay, so now again, I'm going to go over 2 units. I'm going to hit x equals 0, and then that's going to be where the height of that rectangle is. So that height is f of 0, and if I plug in 0 wherever I see an x and f of x, I get back 7. Now go over another 2, hit the right-hand side. And so that area, so we're going to look at f of 2. And if I plug back 2 into the x squared for x, or plug it in for x, I get x squared. 2 squared is 4 plus 7 is 11. Now we're going to go over another 2. So f of 4. Well, 4 squared is 16. 16 plus 7 is 23. One more, go over to 6. hit where the graph hits. So f of 6 is the height. And so plugging in 6 squared is 36. 36 plus 7 is 43. So 11 plus 7 is 18. 18 plus 11 is 29. 29 plus 23 plus 43. Let me just do it here. 15. So that's 95. So 2 times 95, that's 190. So the area under the curve is approximately 190. And technically what we were looking at was this area bounded by this curve. And the blue gave us an estimate of what that was. Let's see if there's questions before we go to part B. So it says, part B says, now take the definite integral using the fundamental theorem of calculus to find the exact area. Well, the fundamental theorem of calculus gave us this easier way to find area under the curve. And that was saying that we can integrate from our lower bound to our upper bound of our function, if our function is continuous and differentiable, dx. And so now, and this is continuous and differentiable, we're looking at an integral from -4 to 6 of our function x squared plus 7 dx. So the fundamental theorem of calculus says this is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, upper bound minus lower bound. And so this one is easy to integrate. We don't need any substitution. Oops, and I don't need to rewrite the integral. So integral drops once we take the integral. So derivative or antiderivative of x squared is x cubed over 3 plus the antiderivative of 7, which is 7x. And we're evaluating this from -4 to 6. We're going to go in and plug in our upper bound first, 6, wherever we see an x. So we have 6 quantity cubed over 3 plus 7 times 6. And then we're going to subtract off brackets because there's more than one term. Now we're going to plug in -4 wherever we see an x. So we need to look at what 6 times 6 times 6 is. 6 times 6 is 36. 36 times 6 is 216. So we have 216 all over 3 plus 7 times 6 is 42 minus, and I forgot my cube right here, -4 quantity cubed. Well, -4 times -4 is positive 16. 16 times -4 is -64. So it's -64 over 3 minus 7 times 4, which is 28. Notice when we distribute our negative, both of those terms become positive. Let's just group first our terms with a fraction. So 216 over 3 plus 64 over 3. And then let's group our integers, 42 plus 28. Well, 216 plus 64 is 280 all over 3. Just checking my work. And then plus 42 plus 28, which is 70. We need a common denominator in order to add fractions. So let's multiply this 70 by 3 over 3. So we have 280 all over 3 plus 210 all over 3, which is 490 all over 3, which we can divide 3 goes into 4 once with a remainder of 1. 3 goes into 19 6 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. So this would be 1/3. So 490 over 3 is the same thing as 163 and 1/3. Which our area we found was approximately 190. So we had an overestimate of that area under the curve and the x-axis. So that other version of the exam, that question was almost identical. It just was worded a little differently. And it said for f of x equals x squared plus 7, answer the following questions. Graph f of x and approximate the area under the curve and the x-axis from -4 to 6 using 5 rectangles equal to the width and the right endpoint. So I'm so happy I chose the right endpoints when I did this. And so we're going to do the exact same thing as we had done over here, figure out how wide our total interval is and divide that by how many rectangles we want. That would give us the base of each rectangle. And we know the area of a rectangle is base times height, and the height of the rectangle is going to be what our right-hand side of that rectangle where that hits the graph. And so we had done that down in here. And then it says now find the exact answer using under the curve using the fundamental theorem of calculus, which is the same thing that we had just done here. So same exact problem, pretty much, just worded a little differently. Okay, so then you had a page of integration, and it said integrate the following. First integral is a indefinite integrals, meaning there's no bounds on there. And the integrand is x to the 4th times the square root of x to the 5th plus 2 dx. So in this problem, we cannot integrate right away. And again, we're going to need to use some U-Substitution. And so let u equal, let's see if I can get this to work. So we can choose u to be what's underneath that square root, which would be x to the 5th plus 2. So when we differentiate both sides, we get du is equal to 5x to the 4th dx. And dx is equal to du divided by 5x to the 4th. So now we're going to go back in and substitute. So we have x to the 4th, and then we have this u, square root of u, what I'm going to rewrite as to the 1/2 power, and dx is the same thing as du all over 5x to the 4th. So notice those x to the 4th cancel, which we needed to happen. We don't want any integrand to have any x left in it. And so we are now in the place where we can integrate. We can factor out a 1/5 if we'd like in front of the integral, u to the 1/2 power du. So antiderivative of u to the 1/2, we're going to add 1 to that. So 1/2 plus 2/2 is 3/2, and we're going to multiply by the reciprocal of our new denominator, which is 2/3. Plus c. So this is 2 all over 15. And then u to the 3/2. Well, let's go back in and plug in what u is. We have x squared plus 2. And the 3/2 power is the same thing as the square root of this cubed. Or we can cube what's underneath the radical. Plus c. So part B, we have 20 all over 2 plus 5x. We don't know how to integrate that. We need to get just one single term in that denominator. So let's u be the denominator, 2 plus 5x. Differentiate both sides. We get du is equal to 5 dx. So dx is equal to du over 5. Going back and substituting, we have 20 all over u, and dx is du over 5. Well, 5 goes into 20 4 times. And so when we take the antiderivative of 1 over u, that was a special case when our exponent, our n, if it's in the numerator, is -1. And that's the case. So recall what you can take the derivative of to get back 1 over u is the natural log of u. This is an indefinite integral, so we have to add c. So we have 4 natural log absolute value of 2 plus 5x and our absolute value plus c. So part C is a definite integral, and we can break this up into 2 separate integrals, but we don't have to really write that out. And so let's just look at this. And let's just take the antiderivative right away. So antiderivative of 8x, add 1 to our exponent and divide. So 8x squared over 2 minus 24. So the antiderivative of 1 over x, again, is the natural log of x. And we're evaluating this from 1 to e. So plug in the upper bound first. And actually 2, let's just simplify. 2 goes into this 8 4 times. So we have 4 all times e, and then it's squared, minus 24 natural log. I don't really need the absolute value because that's positive, of e. And then we're going to subtract off parentheses. Now plug in 1 wherever we see an x. So we have 4, and then we have 1 quantity squared, minus 24 natural log of 1. So 4e squared minus, well, natural log of e. This is saying it's a log, it's an exponent. So it's saying what exponent do I raise my base to of my log, which is e, to get back this e? Well, I raise e to 1 to get back e. So this is just 1 times the 24 here is 24 minus, so let's just distribute while we do this. 4 times 1 squared, that's just 4. So minus 4. And then natural log of 1. Natural log of 1, what do I raise e to get back 1 is 0. So this is just 0. So just cleaning it up a little bit, we have 4e squared minus 28. And part D, it says use the definite integral to find the area between the x-axis and f of x equals x squared minus 6x plus 9 on the interval from 2 to 4. So we need to kind of think about what this graph looks like and make sure, because it says find the area, and we want to make sure that this graph of f of x is above the x-axis the whole time. I know that this graph here, and again, I'm just using some bits of my algebra, but I could be using calculus to do this. I know that this is a parabola. I know my coefficient in front of x squared is 1. So I know my parabola shape faces upwards. If I find my x-intercept, or I factor this, notice that f of x can be rewritten as 2 numbers that multiply to 9 and add to -6 is -3, -3. So x minus 3 quantity squared. This is in vertex form. And my vertex here is at 3, 0. And so this is touching the x-axis right here at 3. And we're going from 2 to 4. So we're trying to find this area in here on this side of the vertex and on this side of the vertex. Because it's above the x-axis that whole time, even though it touches at 0, we we could split this up into two different integrals, but we really don't need to. We can just rewrite this as the integral from 2 to 4 of, and I'm going to keep it in this form because that's the form I know how to take the integral of x squared minus 6x plus 9 dx. So we're just going to add 1 to our power, divide by our new power. So x squared, the antiderivative is x cubed over 3 minus 6. The antiderivative of x is x squared over 2 plus the antiderivative of 9 is 9x. And we're evaluating this from 2 to 4. So plugging in 4 quantity cubed, that's 64 all over 3 minus 4 squared is 16. 16 times 6 is 96. Actually, let's not do that. Let's first reduce. 2 goes into 6 3 times. So how about 16 times 3? And that's 48. So minus 48 plus 4 times 9, that's 36. Minus, now plugging in the bottom bound, 2. So 2 cubed is 8 all over 3. Minus 2 squared, which is 4 times that 3 is 12. Plus 9 times 2, which is 18. So I have 64 thirds. This negative 48 plus 36. That gives me a minus 12. Negative 12 plus 18. That is a positive 6. So when we distribute this, this gives me a minus 8 thirds. And this is going to give me a minus 6. So 64 thirds minus 8 thirds. That gives me 56 thirds. Minus 12 minus 6 is minus 18. I need a common denominator. So 56 thirds minus 3 times 18, 54 thirds. And so this is equal to 2 thirds. Let me see if there's any questions over these problems. Okay, so the other version, version B, same sort of idea, a page of integrals, definite integral. Again, you need to use U-Substitution here. In this case, you're going to let U be what's underneath the integral, the integrand of x to the 5th plus 2. Differentiate. So we get du is equal to 5x to the 4th dx. And then solve for dx, we get dx is du all over 5x to the 4th. So this is the same thing as the integral. Our x to the 4ths are going to cancel when we come back over here, and we're just going to be left with a 1/5. And then this piece here is u, but let's bring it up into the numerator. So this is really u to the negative 1/2 power du. So when I plug this dx back in here, this 5x to the 4th cancels with that 5x to the 4th. Okay, so now it's in the form that we know how to find the antiderivative. So pull the 1/5 out, and then we're going to add 1 to our exponent. So negative 1/2 plus 2/2 is 1/2. Divide by that new exponent, which is the same thing as that's a fraction as multiplying by the reciprocal of 2 over 1. Now all we're going to do, and then we have this plus c, and we're going to go back in and we're going to substitute in what u is. And so we have 2/5 square root, because that 1/2 power is the square root, of u, which is x to the 5th plus 2, and then a plus c. So for part B, we have the natural log of x to the 4th all over x. We do not know how to take the antiderivative of a natural log, and so that's what we're going to choose to be our u to be. We also can use properties of logs, and you don't have to do this, but it will make our life easier by bringing our exponent down front. So that's the same thing as 4 times the natural log of x all over x dx. And so let u equal our natural log of x. So then du is equal to 1 over x dx. Multiply by x on both sides, we get x du equals dx. And so notice when we go back in and substitute, those x's cancel. This x here, when I substitute it, will cancel with that x left in the integrand. So we have the integral of 4u du. So just add 1 to our exponent. So that's going to be 4 u squared divided by that new exponent of 2 plus c. So 2 goes into 4 twice, parentheses, u is the natural log of x, that quantity squared, plus c. Part C, again, the integrand, we don't know how to take the antiderivative of, and so we want to use substitution. And so we're going to let u equal the denominator, 1 plus x. When we take the derivative of both sides, we get du equals dx. And then we can go back in and we can either do direct substitution now or we can do it later. If u is equal to 5, then, if x is equal to 5, then u is equal to, but we don't have x equals 5, it's my vision, x equals 3. That is going to be 1 plus 3, which is 4. Then u is 4. So down here, u equals 4. And then we can plug in x equals 4. So 1 plus this 4 gives us u is 5. Of 1 over u du. Well, the antiderivative 1 over u, that's the natural log of u. And we're evaluating this from 4 to 5. Those are positive numbers, so I don't have to worry about putting in that absolute value there. And we have the natural log of 5 minus the natural log of 4. I would have accepted that, but I would also accept we can do division. Subtraction of logs is the log of each piece, the first 5 divided by the second 4. So D, use the definite integral to find the area between the x-axis and 2x minus x squared over the interval from 0 to 2. So again, I would use some information to figure out what my graph looked like and make sure that that graph is above the x-axis because we're trying to find area between that interval from x equals 0 to x equals 2. I know that this is a parabola. My coefficient in front of the x squared is negative. My parabola is going to face downwards. I also can see where my x-intercepts are. If I factor this and let y equal 0, I have x times 2 minus x. So I know at x equals 0 and x equals 2. So it's facing downwards and it's crossing the x-axis there. And it's symmetrical. I can see that my graph is going to look like this. So I'm okay. I'm above the x-axis from 0 to 2. If not, I would have had to taken the absolute value of the piece below. So we're looking at the integral from 0 to 2 of 2x minus x squared dx. Straight integration. Antiderivative of 2x is 2x squared over 2 minus the antiderivative of x squared is x cubed over 3, evaluated from 0 to 2. 2's cancel there. Plug in our upper bound first. So 2 squared is 4 minus 2 cubed, which is 8 over 3, minus, now plugging in 0, In both places, we get 0. So getting a common denominator, this is 12/3 minus 8/3, which is equal to 4/3. Okay, so you will definitely have a page of integration on the final, and you'll need to be able to find definite integrals, indefinite integrals, and be able to use substitution. So this is the last problem on the exam, and this was version B. It says for f of x equals x cubed and g of x equals 4x, answer the following questions. First, we want to graph f of x and g of x, labeling here graphs. Okay, so I technically meant for you guys to graph these on the same axes, but I was grading some things and that wasn't always the case. And I gave full credit because I didn't state that. But the graphing on the same axis is really going to help you to figure out, which function is on top and which function is on bottom. And so let's first graph x cubed. Well, I know the general shape. If I didn't, again, I can use my calculus. I can find where it's increasing, concavity, max, mins, etc. Or, we can go back to the basics. Let's go in and start plugging in points. And so if x is 0, 0 cubed is 0, 1 cubed is 1, -1, -1 cubed is -1, 2 cubed is 8, -2 is -8. Okay. And so I get this graph, first concave down and then flexion, concave up. That looks like this. And this is our f of x equals x cubed. Now let's graph g of x. G of x is equal to 4x. Well, that's basically, it is a line and it's in the form of slope intercept. So we know that the intercept is 0 and our slope is 4. So if we rise 4, we would go over 1. If we rise 4, we would go over 1. Or if we fall 4, we would go over 1. Fall another 4, go over 1. And so notice when we graph this line, one function is on top between -2 and 0, and one function is on top from 0 to 2. So really when we integrate this, I wanted to find the area bounded between the two curves. We're looking at this piece in here. So that is starting at -2, going to 0. It's always the function that's on top, the bigger y value, which is x cubed, minus the function that's on the bottom, which in our case is this 4x. dx. Plus, now we want to find this area on the right between 0 and 2. Bottom bound 0, upper bound is 2. But this time our function on top is the line. So that's 4x minus the function on bottom, which is this x cubed. And then dx. And we can show where the intersections are, not just by graphing, and sometimes graphing it's kind of hard to see it. We didn't graph right or where they're intersecting, but we can find where they're intersecting by setting those two equations equal to each other. So when is x cubed equal to 4x? Well, let's set this equal to 0. So x cubed minus 4x equals 0. Let's factor out an x. That gives me x squared minus 4 equals 0. That's a difference of squares. So x times x minus 2 times x plus 2. So that's when x is 0, -2, and 2. Which were those points that we were saying? Okay, so now we're just going to go through and we're going to take the definite integrals of each of those and evaluate it. And then we have our area that's bounded between the two curves. And so if we take the antiderivative of x cubed, that's x to the 4th over 4, minus the antiderivative of 4x is 4x squared over 2. And we're evaluating that from -2 to 0. Plus, so antiderivative of 4x is 4x squared over 2, minus the antiderivative of x cubed is x to the 4th all over 4. And that's evaluated from 0 to 2. So upper bound first. So notice when we plug our upper bound for that first integral of 0 in, we just get 0. Minus then now the lower bound, plugging in -2. So -2 raised to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. Even number of negatives is positive, so that's 16 over 4. I'll just go back and reduce it in a sec. Now if I plug in -2 for x here, well, -2 quantity squared is 4 times the 4 out front is 16 all over 2. Plus, now we're going to go in and we're going to plug in 2 wherever we see an x. So 2 squared is 4 times the 4 out front is 16 all over that 2, minus 2 to the 4th power, we said was 16 all over 4, minus, well, now when we go back in and we plug in 0 wherever we see an x, it's just 0. Okay, so let's clean this up. So this is minus, well, 16/4 is 4, minus 16/2, which is 8, plus 16/2, which is 8, minus 16/4, which is 4. So notice inside my bracket here, 4 minus 8 is -4 with this negative out front. So this is +4 plus 8 minus 4, which is 4. And so the sum there is equal to 8. And so if you were doing this and you were in my Math 1A class, you could have used the fact about symmetry. This is an odd function. And so we know that an odd function, we could just look at, if we're looking at area, the area of the one piece and multiply it by 2. Because it's symmetrical, these areas are going to be the same. Okay, so quickly going through this last one. This is on version A. Last problem, f of x is 2x minus x squared, g of x is 2x minus 4, and we want to graph and label our graph. Let's first start with g of x, just because that's the easier one right now. So g of x, this is in slope-intercept form. I see I have a y-intercept at -4, and I have a slope of 2. So if I rise 2 over 1, rise 2 over 1, rise 2 over 1, or I fall 2 over 1. Okay, so here we have g of x. And then let's look at f of x. Well, f of x, again, I can see that this is a parabola, 2x minus x squared. I can see that's a parabola facing downwards. I can find my vertex. There's a couple ways to do it. It's not in vertex form. One way is just go and do straight substitution. Vertex is at -b over 2a, and then we can go in and plug in that x value and figure out what the y value is. Actually, you know what would be faster? Let's just take the derivative. We get 2 minus 2x. Let's find out when this is equal to 0. And so this is when x is 1. We can tell that this is a max because if I take the second derivative, this is equal to -2. And when I plug in 1, this is equal to -2, which is less than 0. And by the second derivative test, this is a max. Occurs here. So if I plug in 1 into my original function, I can figure out what the y value of that vertex is, or the max point. And so plugging in 1 here, I got 2 times 1 is 2 minus 1 squared is 1, which would give me 1. So my vertex, or my max point, is at 1, 1. I can find out where this is crossing the x-axis. I know, again, it's facing downwards. And I'm looking at when is f of x equal to 0. I can factor out an x, which would give me 2 minus x equals 0. And so this is when x is 0 and when x is equal to 2. And this is going to be coming downwards. We want to find out when these are both intersecting each other. I can see by just the graph that it is at x equals 2, but let's look at the other value. So setting both of the functions equal to each other, we're looking at when is 2x minus x squared equal to x minus 4. Let's get everything to one side of the equation. If I add x squared to both sides and subtract 2x, I get positive x squared. But 2x minus 2x cancels, minus 4. When is that? 0. That's when x is equal to plus or minus 2. So it's intersecting down here at 2, -2. And we already saw the positive 2 piece. So we're trying to find this area in here. And so setting up our integral, we're looking at the integral from -2 to positive 2. The function that's always on top on this case is the 2x minus x squared. And then we're going to subtract off the other function, but put parentheses around it, this 2x minus 4. And then we have this dx. So we have -2 to 2. This is going to be a negative x squared here. This is a positive 2x minus a 2x cancels. And this negative and negative, so this is plus 4. So negative x squared plus 4 dx. So all we have to do now is take the antiderivative of that integrand. So antiderivative of negative x squared is negative x cubed over 3, plus the antiderivative of 4 is 4x, and we're evaluating this from -2 to 2. So plug in our upper bound first, wherever we see an x. So we have 2 cubed is 8. So this is -8 over 3, plus 4 times 2, which is 8. Minus, so -2, which cubed is -8 all over 3, plus 4 times -2, which is -8. So you have -8 thirds plus 8 plus 8 thirds. And this is a negative and a negative, so plus 8. So notice our -8 thirds and positive 8 thirds cancel, and then we are left with 8 plus 8, which is 16. Okay, so you should be able to find area bounded between curves on the final also. So hopefully this helps going over that review. You have a review tomorrow for the College Success Center over Zoom. I believe your time is 2:30 to 3:30. The other thing I wanted to share really quickly is I put the exams Zoom test 1 version, the different versions, Zoom test 2, the different versions on the homepage of your Canvas. And so once you get into Canvas, the homepage, just kind of scroll there and you'll see Zoom exams for the semester. And so you have those versions that you can look at and practice with to help you study for this final. Any questions before I turn off the video? So there's 2 different time slots for the video, and that will be at 10:30, and I don't know if she's still around, and sorry, 10 a.m. and 5:30 p.m.